we're going to take a look at gases, liquids, and solids in more detail than we have in the past. In the beginning of the semester, we just defined what they were. And we've looked at, let's see. Well, we've built up our repertoire of atomic structures and symbols and bonding concepts, doing calculations, balancing equations. Now we're going to look at gases, liquids, and solids in terms of a quantitative measure, actually. Okay, so enough being said, let me see if this clicker works. There we go. So we've got several sections to cover, and if we make it through 8, then right down to here, Dalton's law of partial pressures. If we make it to that one, then we'll be doing good. If I'm not too long-winded, then we might move into some other things, and we'll cover those as we go. Next week we're going to have a lab on Boyle's law, so we're definitely going to get into Boyle's law here. Let's see. There we go. I'm learning where all the buttons are. Okay. Let's look at matter, solids, liquids, and gases in terms of some physical properties first, just as a refresher. In terms of volume and shape, how do they compare? How are they alike? How are they different? A quantitative measure of each state. Now, solid, liquid, and gas can be the same substance. It just takes different forms under different conditions. And one of the things that will change is when a substance changes its state, it changes its density. Usually, if you fix the amount of mass, then the factor that changes that gives you a different density is the volume. So we'll have to define that quantitative terms. Compressibility. You know, can you squeeze a solid? Can you squeeze a liquid? Can you squeeze a gas? You probably already have an intuition about which one of those work. And let's see. Oops. Punched the wrong button. There we go. Yeah, we can see that. Thermal expansion. All that means is when you heat something up, what does it do? Well, it always expands. We're going to say, well, why is that? And quantify it as well. All right. So, we must have already looked at volume, shape, density. We're going to look at compressibility now. Just as a refresher, density equals mass divided by volume. Okay. Compressibility is a measure of the change of volume of a substance resulting from a change in pressure. So if you think about it, if you try to squeeze a solid, what's going to happen? Well, under normal laboratory conditions, nothing's going to happen. Solids are generally incompressible. Now, we know from extreme experiments that all types of matter can be compressed. But for our purposes, we can consider solids as incompressible, liquids as almost incompressible. We've actually been able to measure the density of water at extreme depths in the ocean. And it has a higher density, which means less volume per unit mass. So that means it has been compressed at those extreme depths under huge pressures. Okay, then there's the topic of thermal expansion. So, well, I'll tell you what, let me back up a minute. The kinetic molecular theory of matter enters in here. Just as a reminder, the kinetic molecular theory approaches the physical properties of a substance and the way those substances can interact both physically and chemically. And it does so by assuming that all matter is made up of large numbers of small molecules or atoms, and that these molecules and atoms are in constant rapid motion and they collide. Right? So that's the kinetic part, is the motion. And when they collide, we treat them as if they were just billiard balls, right? They bounce off each other, they don't interact. Right? We know that's not true, but for the purposes of the theory and a starting point, we assume that they're just like billiard balls, they bounce off each other. So, what's common to all forms of matter? Well, you got these molecules or atoms moving around, but there's lots of space in between them. Even a solid has enormous amounts of space. Even if the molecules are touching, there's space there that's not being used. Okay, for liquids, the molecules are not fixed in a structure, they're moving past one another. So there's still some empty space in there. Now for gases, there is huge amounts of space between the atoms. So that's why we can explain compressibility in terms of solids are incompressible because they're basically touching one another and it's difficult to push them closer together. It can be done. Liquids have a little bit more space between their molecules, so they're more easily compressed, but not, they're more easily compressed than solids, but not easily compressed. And then gases, with all that space between the molecules, it's easy to compress a gas. You just move the molecules closer together. Okay, that takes care of compressibility. How about thermal expansion? Thermal expansion is the measure of the change in volume of a sample resulting from a temperature change. That's why we call it thermal expansion. So what's happening when you increase the temperature of a substance? You're putting energy into it. If you put energy into something, the molecules are going to move faster. And when they strike one another, they strike with more force, which drives them further apart. So if you increase the amount of energy, according to the kinetic molecular theory, increasing energy makes them strike and move further apart. So they tend to expand. And they go a further distance before they strike their neighbors. Okay, this table came straight out of your book. It's table 7.1, and it describes characteristics of solids, liquids, and gases. So we have, let's see, there it is. We can say something about volume and shape, right? So solids have a definite volume and a definite shape. We know that. Liquids have a definite volume, but an indefinite shape, which means they need a container. But if you put them in one container that's calibrated, it will measure a certain volume. If you put them in a different container that's calibrated, it'll measure the same volume, even if they're different shapes. Gases, on the other hand, have, let's see, just a second. Oh, there it is. There it is. One second. I don't understand why I have that. I wonder. Oh, okay. I'm still figuring this thing out. Okay, so here we go. Gases have an indefinite volume and an indefinite shape. They cannot hold their own shape. So if you put a gas in a larger volume, it will expand to fill that space. It will change its volume. Density. Solids generally have a very high density. Liquids usually have a slightly less density. They occupy a little bit more volume for most liquids, not for all. There are some exceptions, notable of which is liquid water and solid ice, that the relationship is inverted. In other words, ice is less dense than liquid water. But for most transitions from a solid to a liquid, the density decreases. And then when you get to the gas, you have a very, very low density. Because for the same amount of mass, occupies a huge space. And a rule of thumb we used to use concerning the evaporation of a liquid to a gas is the ratio of volume is about 1,000 to 1. Now there's a wide range depending on the substance, but generally speaking, a gas will have expanded 1,000 times over the volume of the liquid for which it originates. And that actually is one of the sources of explosive power for high explosives. They rapidly change from a solid or a liquid or a paste or whatever the case may be into a gas very quickly. And that sets off a blast wave. An increase of volume from this to that very quickly provides a lot of the force of the explosion. That in addition to release of energy. Okay, so let's see. Bomb shape, density, compressibility. We mentioned this earlier. Small compressibility for solids, if any. Small for liquids, maybe a little more compressible. And then huge, very large compressibility for gases. Why? Because there's lots of space between the molecules. You just move them closer together. And that's your measure of compressibility. And then thermal expansion. Solids generally have very small thermal expansion. For every degree centigrade, you may get a 100th%, just very small. And it varies widely among solids. I can remember as a kid spending some time on the railroad lines and looking at the tracks, and every so often, you know, I forget how far apart it is, maybe 10 or 20 feet or so, there's a gap between the rails, and there's a bolted segment holding the rails together. And they always have a gap between them, more so in the winter than in the summer, because when they heat up, they expand and they close that gap. So they put that expansion joint in there for the purposes of not buckling the rails when they heat up. But by the time I was maybe 14 or 15, I started seeing rails that they were continuous for a mile. You just walk down there and you eventually find a joint, but it'd be a long distance. What they had done was they had changed the formulation of the steel in the rails to reduce this thermal expansion. So the new steel would not expand as much for a change of 1 degree Celsius. Okay, liquids. Liquids are, they generally have a small thermal expansion, but it's a little more than solids. And then gases have a moderate thermal expansion. Okay, those are general characteristics. Physical properties. This, I thought I had given you the kinetic molecular theory in the past. Maybe I didn't. So I was telling you something, I was describing something that you hadn't been introduced to before. So we'll hit it again. These are the main postulates of the kinetic molecular theory. Matter is composed of tiny particles. I mentioned that earlier. And they could be atoms, they could be molecules, they could even be ions that have a definite and characteristic size that does not change. So these billiard balls are a fixed size, and there are lots of them. They're very tiny. The particles are in constant random motion, right? And the reason we have to say that is because there are so many of them, we cannot track each individual atom or molecule to determine the outcome of a particular state and a transition to another state or to another set of conditions. You'd have to know the nature and the direction, the momentum, mass. You'd have to know the momentum, mass times velocity of every particle in order to predict its outcome, right? And not even our supercomputers can do a good job of that. So we just say, all right, they're random, and we're going to treat it statistically, right? What's the most probable outcome? We can say that they're in random motion and they have kinetic energy, right? Because they have mass and they're moving. And we use this particular formula. Kinetic energy equals 1/2 mass times velocity squared. So every particle has kinetic energy. Okay, the particles interact with each other, and we have to assume well, the basic postulate of this theory is that they behave like billiard balls. But we're going to take that starting point, and now we're going to say, okay, we know for a fact that when a molecule approaches another molecule, or atom approaches another atom, whatever the case may be, an ion approaches another ion, there are either repulsive or attractive forces involved. And we're going to divide those up into these two conditions. Potential energy. It's a stored amount of energy. And it could be based on several things. Like it could be based on the position, right? We have gravitational potential energy. If I change my position from here, if I climb stairs or a ladder, and I go to the next floor, I've added to my potential energy. Simply by my position. How do I get that energy back? I just come back down the stairs, or I jump off the roof, or whatever the case may be. And you get all that energy back. It may not be in the form you want it, but you'll get it back. Or it could be some condition that's described for that substance, for that molecule. Let's see. It may have potential energy based upon its temperature. Right, so, and it doesn't have to move. If it's solid, it's not going to move unless it melts. So as long as it's a solid, it's going to sit there and vibrate. And you add more heat, it'll vibrate even further. Eventually, it'll break bonds with its neighbors and separate. Or it may have potential energy based on its composition. Right? For instance, nitroglycerin. Nitroglycerin is, let's see, Those are carbons. And let's see, glycerin's going to have, let's see, C. Glycerin is like this. And all these others are hydrogens. Okay, that's glycerin. And then nitroglycerin, we combine that with nitroglycerin. No. Yeah, I'm painting myself into a corner. Suffice it to say that nitroglycerin has a lot of stored up energy based upon its composition. So when it decomposes, it gives up a lot of stored energy. That's potential energy. You can have potential energy not just within the individual molecule, but between molecules. And one of those, the most commonly described one, is electrostatics. So if you have two ions at the same charge, you try to push them together, they're going to repel one another, kind of like north-north on magnets. Push them together, they push away. If you push them closer together, you got to add energy, store energy, and if you hold them there, they've got that stored energy, and you release it, they're going to fly apart and give you back that energy. Or they can have an attractive energy, right? They can have a positive and a negative ion that start off close together. If you try to pull them apart, they'll resist because there's attraction. And if you pull them apart like that, you stored up energy in that attraction between them. And if you release it, they'll slam back together, you get the energy back, either way. Now, that references electrostatic interactions for charged particles, but the electrostatics don't have to be between constant charges, complete charges like for ions. They can be intermittent. And I think we mentioned that at some point in the past. If we didn't, I want to tell you again. These charges, slight charges, right? When we talked about polarity of molecules, right? They can have less than a complete charge, or they can have charges that come and go. All right, fourth postulate for the kinetic molecular theory of matter. All the particles have kinetic energy. They're not just in constant motion. We can assign kinetic energy for each particle. If we knew each particle's mass and its velocity, we would be able to assign kinetic energy for each particle. And it's largely dependent, in fact, it's completely dependent upon temperature. The higher the temperature, the more kinetic energy. When these particles collide with one another, they transfer energy. They may, for a split second as they interact, right? They store up energy as they interact, they stop, and then when they fly apart, they get that kinetic energy back. Okay? So it's the interchange of kinetic energy and potential energy. Now, when we say they collide elastically, that means when we're saying an elastic collision, the kinetic energy is conserved. That is, the total kinetic energy of these two particles, when they approach one another, like if this one's moving that way and this one's moving this way, when they collide, the kinetic energy of this one and the kinetic energy of that one, when you add them up, the total before collision is the same as after collision. That is an elastic collision, like billiard balls. Or I think they still make them, what do they call them, super balls? You can drop the ball from here on a hard surface and they'll come back almost to exactly where it was. So it gained kinetic energy due to its gravitational position. And when it hit the floor, it had a certain velocity, and then it had an elastic collision with the floor, and it got its kinetic energy back and helped it rise to that same level before you dropped it. Right? All of that is conservation of energy, kinetic energy. And actually, before it moves, it has no kinetic energy. It has potential energy. And when it hits the floor, right before it hits the floor, as all of that potential energy is converted into kinetic energy. And then it converts that kinetic energy in this direction to kinetic energy in that direction, comes back up potential energy again. That would be perfectly elastic. Okay. Now what we're going to try to do is to explain the differences among solids, liquids, and gases in terms of kinetic energy and potential energy. And the potential energy we're going to focus on is electrostatics, because when we change phases from solid to liquid to gas, it's the interaction of molecules that matters, not their internal potential energy. Right? We're assuming that that doesn't change. So that one is written out of the equation. And now we're only interested in the kinetic energy that's available to them due to temperature, and the potential energy that's available due to attraction when they get close together, or repulsion, whatever the case may be. So there's a balance. We're looking for the balance between kinetic energy, which we consider to be a disruptive force, because the faster something is moving when it comes together, the less time there is for the potential electrostatic attraction to take effect. So it's a disruptive force. It overcomes the attractive forces. And the potential energy is what we would call cohesive forces. So there's a difference here between the kinetic energy referencing disruptive force and the potential energy cohesive force. So what we're looking for is which one dominates. Does the kinetic energy dominate or the potential energy dominate? And that determines whether you have a solid, a liquid, or a gas for any particular substance. Okay. Kinetic and potential energy, right? We mentioned that. Okay, for solids, the physical state is characterized by a dominance of the potential energy. The cohesive forces are strong enough to hold it together. And the kinetic energy is not strong enough to disrupt it. Okay, so the cohesive forces, the potential energy is dominant. And they generally form, well, actually there are two types, two subcategories of solid: crystalline solids and amorphous, AM, amorphous. Or crystalline. Crystalline solids have a regular structure that repeats itself. And if you grind up a big cube of solid, sodium chloride, you'll find a whole bunch of loop cubes, right? The structure, the internal structure is regular. So no matter how far down you go, until you get to individual ions, of course, you're going to have that same cubic structure. That's crystalline solid. Amorphous solids don't have any form that's repeatable. For instance, glass is a good example of that. Glass is an amorphous solid. In fact, some researchers say it's a supercooled liquid. But in any case, it's amorphous. So each particle occupies a fixed position, and if it has any kinetic energy at all, it's related to vibration. It stays put, but it can vibrate. And there's some motion energy in there, but it's not enough to break that cohesive force. Example. These little lines around here, they're meant to illustrate vibration. So for that reason, solids have a definite volume, right? Because they're strong cohesive forces, and they have a definite shape. They can hold their own shape. And they have a high density because they're drawn close together in this regular structure, or irregular structure, as the case may be. They're located very close together. Many of them are touching. Some of the particles of a solid may not be touching maybe one or two of their neighbors, not all of their neighbors. It just depends on, it's a very complex subject, so we're not going to deal with that right now. But the free space is at a minimum. And they have very high density and very small compressibility because there's very little space between the particles, not much space at all. A very small thermal expansion. If you increase the temperature, you want to see expansion. Well, you get some, but not much, because the disruptive force is still not enough to overcome the cohesive forces. You just get more vibration, and if they're vibrating, they may push each other apart a little bit. So you get that very small thermal expansion. Okay. So what happens with a liquid? Well, with a liquid, you've got enough vibration now that you start to overcome those cohesive forces. I mean, it's not complete. There's sort of an uneasy balance between potential energy and kinetic energy. The cohesive forces and the disruptive forces are about equal. The particles can move past one another, but they still interact on their way. They're about the same magnitude here. They're randomly packed, and they can move past one another with ease. So here's an example. There's a liquid in this container. It does not have a definite shape because the particles can easily move past one another. So they would spread out. So I pour that liquid out on a table and it would spread. It needs something to hold it together. But it wouldn't spread far enough so that it would change the volume of the material. That still remains constant. Okay. So what we're saying is these attractive forces, let's see if I can use my. These attractive forces are strong enough to restrict the particle's movement to within a certain volume. But they're not strong enough to hold them in place. so that they still have some random motion in that fixed volume. They have reasonably high density, right? Similar to solids, a little lower density than solids normally, because they're not widely separated. They're still touching one another from time to time. Okay, they have very small compressibility also because they're still close together. An increase in pressure doesn't squeeze them together much closer. It will some, right? Like I mentioned earlier, we do have evidence that water at depth in the ocean does compress. And we've duplicated it in the laboratory also. Okay. Very small thermal expansion. A little more thermal expansion than solids. Why? Because now the cohesive and the disruptive forces are about equal. So if you add a little bit more disruptive force, you're going to start getting them to move further apart. So a thermal expansion for a liquid is a little bit larger than it is for the solid of that substance. Okay, enough said about that. Now for gases, the physical state of a gas is dominated by kinetic energy. Right? The disruptive forces are much, much larger than the cohesive forces. So the molecules are very far apart with very high kinetic energy for each particle. The attractive forces are very weak. And the particles essentially move independent of one another. Okay. Now we're going to take advantage of that when we start talking about the gas laws, because the gas laws treat gases as if the particles aren't even there. They're just space. And we can do that because there is so much space between them. The size of the particle and the interaction of the particles is insignificant. There's your artist's rendition of a gas, right? Lots of space between the molecules. And they're moving at very high velocity because they have lots of kinetic energy. So as a consequence of the dominance of disruptive forces in a gas over the cohesive forces, the gas has an indefinite volume and indefinite shape. Right? It cannot maintain its own volume, cannot maintain its own shape. It needs a container. And it will keep expanding until it fills the space. There needs to be something to restrain it. Now, that could be a closed vessel in the laboratory situation, or it could be gravity holding the gas in a certain volume around the planet. Like planet Earth, for instance. They have very low density. Why? Because for a given amount of mass, they occupy a huge volume. So, well, I erased it. If you increase the size of the denominator, mass divided by volume, increase the denominator to a huge amount, the density decreases to a very small number. Okay, so that means when you compress a gas, there's lots of space, right, between the molecules. All you have to do is just move the molecules closer together. So pressure will compress a gas very easily, right? That's how we fill our tires. Well, our bicycle tires with a pump. You just apply pressure and you force air into that same space. Or you have a fixed amount of gas and you just decrease the volume, apply pressure, decrease the volume. Now the molecules occupy a smaller space, so their density should increase because the volume has decreased. Thermal expansion. The particles increase in velocity, which increases their kinetic energy, which means when they collide, they're going to move farther apart more quickly. So you are adding space to the gas if you allow it to expand as you add heat, as you increase the temperature. But there's so much space between the molecules already that when you increase the temperature, you increase the space some. And we're actually going to describe a law that governs that change in volume, thermal expansion. It's called Charles' law. I'll tell you again in a minute. Okay. Physical states, gases, liquids, and solids. All right. Now we're going to talk about the gas laws. Historically speaking, well, if we go back into the Middle Ages, we'll see alchemists working with liquids and solids primarily, some gases. But when we move into the modern era in, say, 17th century, quantitative experimentation lent itself better to the technology of the day, to the study of gases. So that's why we have gas laws that preceded investigations, scientific investigations, quantitative investigations of liquids and solids. We needed to understand gases first. So we get these mathematical expressions for the gas laws that describe relationships among measured quantities. Now, when we describe a gas, we only need 4 quantities. We need pressure, volume, temperature, and moles, the number of particles of gas. If we know these 4, we can describe its behavior perfectly for the ideal gas. Let's put it that way. Okay, I'm going to just a reminder here. Early on in the semester, we drew a distinction between laws and theories. Okay, now we're talking about laws, and all these equations do is describe what happens. Doesn't say why something happens. The kinetic molecular theory explains why things happen. But we're going to talk about laws now. Just what happens. Okay. If we want to look at the relationship between any 2 of these, pressure, volume, temperature, volume, moles, or any combination, if we relate 2 of them and if one varies, how does it affect the other? If that's our goal, then the other 2 that we're not investigating must be constant. If they're not constant, then you've got too many variables. We only want to look at how one varies with the other one in the beginning. In fact, that's historically how it was done. And the first investigation was between pressure and volume. That means temperature and number of moles must be held constant. Okay? If we're going to investigate pressure and volume, we have to define our terms, right? So how do we measure pressure? Well, pressure by definition is equal to a force per unit area. So if I have a, let's see, I don't know, a 1 foot square with a rod on it, and I push down on that rod, then I'm applying a force over that area against whatever, against the floor, against the table, against a gas. It's force per unit area, okay? Well, in the SI system, force is in units of newtons, okay? And area is a derived quantity from meter. Meter is the standard length, so square meter would be the standard for area. Newtons per square meter, okay? Well, we have a derived unit from that. Instead of saying Newton per square meter, we say Pascal. Okay, 1 Newton per square meter is a Pascal. But those are useful quantities in some cases. But we're going to use something that's a bit more historical. These were derived later. Earlier, pressure was defined in terms of a column of mercury by the Italian scientist Torricelli. He invented the barometer. The barometer measured air pressure in terms of how high will a mercury column rise against a vacuum. And let's see. Let me check my hard copy so I won't steal my own thunder. Yeah. Okay. I've got a slide on that barometer in just a second. But what we're going to say is, in fact, before I talk about this, these are all units of pressure, right? And they're useful. In fact, we're going to use this one next week, pounds per square inch. We're going to use this one, and we're going to use this one. Okay. Let's look at the, let's see, let me move ahead. Oh, that's a good question. Which one of these measurements actually contains force per unit area, right? We can't see force per unit area in these in 1 atmosphere, millimeters of mercury, or torr, which is exactly equal to a millimeter of mercury. Pounds per square inch, that is force per unit area. The SI units for, that's not right. Kilogram is a mass, it's not a force. Right, so there's an error in the slide, I think. All right, before we get to a further discussion of the units, let's think of a gas in terms of what is it doing inside that enclosed space? Well, according to the kinetic molecular theory of gases, those particles are moving fast and they're bouncing against each other. But what else are they doing? They're bouncing against the walls of the container. If they weren't doing that, then we would not know that the gas was in there. All we have to do is screw a gauge into a tiny hole in that container, and we can measure pressure that's inside the container. Why? Because those molecules are banging into our pressure gauge. There's a little diaphragm in there that responds to being hit by those molecules. If that were not the case, then we wouldn't be able to measure pressure. It would be sitting on 0 and not move. So, according to the kinetic molecular theory, those molecules are banging up against each other and the walls of the container. Now for Torricelli. Torricelli had limited technology. At that time, technicians, and probably Torricelli himself, were very good at producing glass tubes with a constant diameter, an inner diameter. That was easy to do. All they had to do was just heat one end of it and close it off. Now you've got a tube with one end open and one end closed. So what Torricelli did was he upended this tube, filled it with mercury, and then put his thumb over it, or his hand, whatever the case may be. And then he inverted it and submerged it in the pool of mercury. And then took his thumb off. And what happened? Well, you might expect, if you were a researcher, you might expect that mercury would go all the way down to the same level here. But it didn't. Why? Because there was a balance of forces required. There was force being applied here from the atmosphere. And there was a force being applied here from the mercury. And they were pushing against each other. So the atmosphere was pushing on this, and the only force that was being balanced here was the mass of that mercury. What we know here is that that was the first vacuum. Define a vacuum. A space, a volume, that used to contain some matter, and now it doesn't, right? That used to have matter, now it doesn't. That's a vacuum. So he noticed, Torricelli, he noticed that if he put this barometer in the back of his octocart and went up the mountain, that the mercury dropped. And if he went from where he was located down to the ocean, it went up. He reasoned that the reason for that was at high altitude, there was less air above him pushing down on the pool. True. He moved down, he went down to the ocean, sea level. Now there's more air above him pushing on this pool. So the column went higher. And he used that to measure air pressure. It didn't take long for other scientists to take advantage of this invention. Some of them just sat him on the table and just watched him over time. And they correlated a movement of the mercury to a lower level, bad weather, to a higher level, good weather. And we still do that today. High air pressure means good weather, or increasing pressure as it starts to move up means good weather's on the way. Pressure's dropping, that means bad weather's coming. Okay, so what unit of measure did he use? Well, by that time, they knew meters and millimeters. So he just marked it off in millimeters, and how high was the column from this level of the pool? That was his measure of air pressure, millimeters of mercury. And we use that measurement even today. If you go to the doctor's office and get your blood pressure checked, your systolic divided by your diastolic is in millimeters of mercury. That's your blood pressure. It's a modification of this device. Okay. But of course, that's not measuring air pressure, that's measuring blood pressure. And we don't have time to discuss that in any detail right now. So I'm going to move on. So that's one way to measure air pressure or gas pressure is millimeters of mercury. Okay. So the four variables are pressure, volume, temperature, and moles. Molar amount. All right, let's go to Boyle's law. Oh, before we do that, remember that earlier slide. 760 millimeters of mercury is now taken as the standard for 1 atmosphere pressure. At sea level, this is the average pressure. It's 1 atmosphere. This is also equal to, Torr, in honor of Torricelli. 1 atmosphere is also equal to 14.69 pounds per square inch. Okay. And let's see, there was one other one. Maybe that was it. Let me back up and see. Yeah, that's it. Okay. So now that we have a way to measure pressure, and we know how to measure volume, volume is in liters or milliliters, whatever the case may be. Boyle, Robert Boyle, was an Englishman. And he took Torricelli's invention and used it, the concept anyway, to measure pressure on a trapped gas versus the volume of that gas. And the way he did it, let's see, I steal my thunder. No, okay. The way Boyle did it was he used what he called a J tube. So he had a glass tube that was bent. Let's go a little higher. That was bent, and it was closed on this short end. Go and open up here. Okay. So into this J tube, he poured mercury. Okay. And he put a little bit of mercury in there and it cooled up on the bottom right here. Okay. Put a little bit more and it cooled up higher. And put some more. Eventually, it touched the inner radius of that curve. And when it did, that means all of this gas in here is now trapped. Right? And if you keep pouring mercury into it, it's got the same amount of gas in there. Right? That doesn't change. Temperature. If you conduct the experiment fast enough, the temperature won't change. If you want to be sure that the temperature is constant, all you need to do is submerge this thing in water, right? Which will stabilize the temperature, or even better than that, ice water, which is very stable. As long as you've got solid ice, liquid water together in the same space, once they come to equilibrium, their temperature is 0 degrees Celsius. It won't change. But whatever the case may be, he kept adding mercury. And as he did, he found that he might get this much mercury in here, but it only came up to here on that side, right? They weren't the same height. Since they weren't the same height, he reasoned that this gas was pushing back against the mercury to hold this one higher. So as he increased the pressure, the volume of the gas decreased. And the pressure in millimeters of mercury is the difference between this one and this one. That height is the pressure on the gas. And then the volume of the gas was relative to how high is this. He knew that the inner diameter of the tube was very good, was very constant. So all you have to do to change the volume of a cylinder that is constant diameter or area is change the height, right? Remember the volume of a cylinder? Is height times area. So if the area is constant, all you need is the height. Okay, so what Boyle did was he measured this difference in height, this difference in pressure against the volume that was trapped. And he just set up a chart. That pressure, volume, right? Measured pressure, volume, pressure, volume, pressure, volume. As the pressure went up, increased, the volume went down. Okay? So what he discovered was that the pressure that he measured times the volume of the gas at that particular time was always constant. So he said pressure times volume is a constant. Okay, that's Boyle's law. And this is pressure one, this is pressure one, volume one, and this is constant. And then he measured it again. The second pressure times the second volume is equal to the same constant. Okay, but by definition, that's a constant. So what do we know, mathematically speaking? If this is equal to K and that's equal to K, then they're equal to each other. So this is the expression we typically use. Pressure times volume under one set of conditions for the same gas. If we change one of these, then the product of those two values is equal to the original product. So this relationship says that if you know three of these, you can calculate the fourth one. What else does this say? This says that pressure times volume, one goes up, the other goes down. That's an inverse proportion. Anytime you have a product of two variables equal to a constant, that's inverse proportion. Because if one goes up, the other has to go down in order to keep that constant. Right? That's an inverse proportion. So there's your first useful equation. P1V1 equals P2V2. Boyle's law. Let's see, I didn't mean to do that. Temperature, moles. Okay. So this illustrates that concept. At this pressure, let's see. At this pressure and that volume, if we multiply those two together, 100 times 8 is 800. If we decrease the volume to 4 liters, that means the pressure has doubled. So 200 times 4 is also 800. If we increase the pressure further, it decreases the volume to 2. So 400 times 2 liters is 800. The product of those values are all equal to the same number. They're constant. All right, so which of the following is the correct equation for Boyle's law? Well, P1V1 equals P2V2. That says this one right here. Okay, but notice P1 V1 equals P2 V2. If you want to solve for one of these unknowns, say you know this pressure, and this volume, you want to find the original volume. So just solve it. P2 V2 over P1. plug in your numbers, and you get your answer. Now, it doesn't matter what units of measure you use in this case. Pressure could be in any units: PSI, pounds per square inch, millimeters of mercury, atmospheres. Volume can be anything. As long as the volume is the same on both sides and the pressure is the same on both sides, you're good to go. This law is very forgiving of units of measure. Okay, so we're going to do an example here. A sample of helium gas occupies 12.4 liters at 23 degrees C and 0.956 atmospheres, right? It's less than 1 atmosphere, just a little bit less. What volume will it occupy at 1.2 atmospheres? Increase the pressure. What should happen to the volume? Right? Pressure goes up, volume goes down. Assuming that the temperature stays constant and the sample, of course, doesn't change. We have the same number of moles. Right? So here's what I do with these types of problems. I extract that information from the word problem and put it in a formula format. We know that this is going to be a before and after situation. We know we're given the before conditions, 12.4 liters and 0.956 atmospheres. We're given part of the after conditions, 1.2 atmospheres, but we're not given the after volume. So if you do this, volume, pressure, volume 2, pressure 2. This is to keep you from putting the numbers in the wrong place, because if you put them in the wrong place in that formula, you get the wrong answer. So what's the original volume? 12.4 liters. What's the original pressure? 0.956 atmospheres. Okay. What's the final volume? That's the question. And what's the final pressure? 1.20 atmospheres. Okay. Atmospheres, atmospheres. Same units of measure for the pressure. That's important. Volume is in liters, so the answer will be in liters. And now you can plug these values into that formula and solve for the unknown. Right? And that's what this formula tells you. Now that we know which is which, let's see. Now that we know which is which, we can put them in the right place and get the right answer. 9.88 liters. Now, does that make sense? Well, let's see. We increased the pressure and the volume went from 12 to 9.8. That's reasonable. The volume, we expected the volume to go down. All right. That was Boyle's law. Pressure, volume relationship. P times V equals a constant. Now, what if we want to see the relationship between volume and temperature? Now we have to hold that one constant and that one constant. This is Charles. He was a Frenchman. Now, why did Charles' law come along after Boyle's law? Because in Boyle's day, they didn't have a reliable measure, a unit of measure or a device that would reliably measure the temperature of any substance. The temperature scales hadn't been invented. So once those temperature scales were invented, now we have a way to measure the temperature of the gas, and we've always had a way to measure the volume. So now Charles said, okay, I've got the tools. I'm going to measure volume temperature relationships of the gas. I know I need to hold pressure and moles constant. When he did, what he found was the relationship of volume to temperature is equal to a constant, the quotient of volume to temperature. is a constant. So what does that tell us? If this has to be constant under all circumstances, moles and pressure being constant, we're not changing those, then if the temperature goes up, the volume has to increase also. You have to get expansion of the gas. If the temperature increases, the volume must increase. Mathematically speaking, that is a direct proportion. Not an inverse, but a direct proportion. And anytime you have a quotient in this relationship that's equal to a constant, those two variables are in direct relationship to one another. They have to be. Otherwise, that won't be a constant. Okay? And we use the same reasoning as before. If this V1, T1 relationship is equal to the same constant, then they have to be equal to each other. That's math also. Okay. I forgot to turn my silencer on. There we go. That won't happen again. Okay. Here's the thing. For Charles' law, he could deduce the relationship here, but he couldn't quantify it until he made sure that the temperature could never be negative. Right? What would happen if you had a negative temperature? If the initial volume was maybe 20 degrees Celsius and the final volume was minus 20 degrees Celsius. You come out with a negative answer. You can't do that. Not in the real world. He needed a temperature scale that was always positive. That's the absolute temperature scale, Kelvin. Degrees Celsius plus 273 is Kelvin. And that will always be a positive number. So whenever you're working with temperatures, from now on, well, I can think of some exceptions, but let's say for gases, when you're working with temperature and gases, it always must be Kelvin. You have to convert Celsius to Kelvin. And if you don't have Celsius, say you have Fahrenheit, convert Fahrenheit to Celsius, right? We've done that before. Then convert Celsius to Kelvin. Then you can use the temperature in this equation. He noticed that and here we have a constant force, the same force applied to each one, right? If all of these forces are the same and the diameters are equal, then the pressures are the same. There we have constant pressure. The number of moles are the same as long as there's no way for that gas to get in or out of that space. Good seal, no valves. As long as you've got the same amount trapped in there, moles are constant. Now we can say, what's the relationship between volume and temperature? If you start off with 2 liters of gas at 100 K, which is actually pretty low temperature, and you double the temperature from 100 to 200 K, then the volume will double also. Or if you quadruple from 100 to 400, then the volume will quadruple from 2 to 8. So the quotient of all of these numbers is constant. 100 divided by 2 is 50, 200 divided by 4 is 50, 400 divided by 8 is 50. Okay. Which law states that the volume of a fixed amount of gas is directly proportional to its Kelvin temperature at constant pressure? That would be Charles' law. Okay, here's an example. And we do the same thing here as we've done before. Set up. Well, first you have to decide what type of problem is this. Do you know the before conditions and the after conditions? If you do, then you can use that special version. I need a new marker. You can use that special version of Charles' law. Okay, so you set up your table, right? Volume 1, temperature 1, volume 2, temperature 2. And then you plug in the values. First of all, your balloon contains 1.44 liters, 1.3 liters at 24.7 degrees, placed in a beaker of liquid nitrogen, which is really cold. Wait a minute, that's not right. This is dry ice, so that's wrong. Placed in a beaker with containing solid carbon dioxide. Liquid nitrogen is minus 195. Right? So that can't be. That's a mistake in the slide. But we're going to use that temperature. The initial volume is 1.43 liters. The initial temperature is minus 78.5 plus 273. That's your Kelvin temperature to start with. Oh, no, I'm sorry. That's the final temperature. Minus 78.5 plus 273. The initial temperature is 24.7 plus 273. Okay. And then this is the answer. Okay. I think there's more to this slide here. So let me get this out of the way. There we go. So once you've got your data assigned to the variables, then you can plug it in the equation. And here's the conversion for Kelvin before, volume before, temperature after, and volume after, and we solve for the temperature. Okay. If the temperature decreases from 24.7 to minus 78.5, then the volume will decrease from 1.43 liters to 0.85 liters. That's reasonable. That is consistent with the law. All right. Now, there's one law that we left out. And I thought I had modified these slide sets to include it. Maybe I picked up the wrong one. I'm going to give it to you anyway. There's no slide for this one. What if, before we get into that one, what if you want to investigate volume and moles, the relationship there? Then temperature and pressure have to be constant. If we do that, then we get a relationship where we have the volume before of this many moles is equal to a constant. So it's also equal to the volume after if you increase the moles or decrease the moles to this new value, right? Volume and number of moles are directly related. They're directly proportional. So you increase the moles, you increase the volume, as long as you hold the pressure and temperature constant. This is Avogadro's law. And the reason I want you to know that one is it's absolutely crucial to the advancement of chemistry through the middle of the 19th century. The chemists had hit a roadblock. They understood chemical reactions in terms of masses. Mass of this reactant plus the mass of this reactant yields products. But the problem was, and we know from balancing equations, that reactions don't occur based upon mass-mass relationships. They occur based on mole-mole relationships, numbers of particles. But the chemists in the middle 19th century didn't know that. So when something went wrong in their reactions, they didn't know how to fix it, right? If you were working for a university, then your research project might go down in flames. Or if you were working for a company and you were making a product that was being sold and the reaction went wonky and you couldn't fix it, you were the chemical engineer that was responsible. If your boss kept you on, if he didn't fire you, then he would be losing money. So a bunch of academics and chemical engineers got together in 1865 at a place in southern Bavaria called Karlsruhe. There's a university there. So they met for a week or so, maybe 2 weeks, I can't remember how long, trying to figure this thing out. And they had bunches of speakers come and talk to them about what they knew. And there was one, his name was Cannizzaro. See if I can spell that right. I think that's right. He was an Italian. He was a student of Avogadro. And he had acquired the knowledge that Avogadro had proposed, this relationship. And what he did was he incorporated that into a chemistry lab manual, a textbook for his students. He wrote his own textbook. And his approach was chemical reactions are not mass-mass, they're numbers-numbers. And that's how he taught his students. And he published a paper to that effect. And he gave Avogadro credit for the original, the thought process that brought him to that point. Well, he was at the conference and he presented his paper and nobody could agree on how to fix the problems. So they all just kind of threw up their hands and left. But Cannizzaro was at the door as they were leaving, handing out copies of his paper. And they politely took the paper and went back to their universities and companies and spread out all over Europe and read the papers. And light bulbs started going on all over Europe. They said, that's it, that solves the problem. Okay, how does it solve the problem? Here's how it solves the problem. Avogadro says, if you have two volumes of gas and the volume of this one equals the volume of that, and it doesn't matter what gas is in each, it's totally irrelevant. And they're at the same pressure inside. Okay? They're also at the same temperature. Okay? If all three of these conditions are equivalent for those two gases, then the number of moles in this gas equals the number of moles in that gas. Exactly equal numbers. Haha. Since it doesn't matter what the gas is, if you have the two gases in here that are different, then their masses are not going to be equal. So now we know if they have the same number of particles, but they have different masses, what do we know about each one of the particles? each one of the particles has a different mass, and we can relate them to each other. Now we have a way of getting a handle on numbers of particles. And when we go into do chemical reactions, if we know the numbers of particles that are reacting together, now we can solve the problems. Okay. So that was Avogadro's law. And this would be the equation relating volume and moles, volume and moles. You can solve individual equations like that. But what we're doing with the combined gas law is we're putting these together. If we have a pressure-volume relationship, pressure 1 times volume 1 equals pressure 2 times volume 2, we have Boyle's law, right? But if we're wanting volume, like that, we have Charles' law. So if we put those together, we have Boyle's and Charles together. But if we also include the relationship of volume and moles, we have N1 here and N2 there. So that is the combined gas law. PV over NT, P1V1 over N1T1 equals P2V2 over N2T2. So if you're given a problem where you know all of these conditions, except for one, they can all vary through the experiment, before and after. They can be all different. And one is unknown, you can solve for it. So all of these gas laws up to this point, we've presented in terms of before and after. You have to know the conditions before and after, absent one variable that you solve for and answer the question. Okay, so the mathematical expression for the combined gas law is that one. And you can solve it for any of the unknowns. Actually, based on the slide, the previous slide, that's correct. But we know also that there should be moles incorporated there. Okay, so here we have a situation where at what temperature does 121 milliliters of CO2 at 27 degrees and 105 atmospheres occupy a volume of 293 milliliters at a pressure of 1.4. So in this case, we're talking about three different conditions that are varying. Right? Temperature, which is unknown, volume, and pressure. So you set up your P1, V1, T1, P2, V2, T2, and fill in your values, find out which one is missing, and plug it into the equation. Now in this case, the number of moles didn't change. Right? So if we have this equation, and moles is constant, then that one goes out, right? Because they cancel one another. They're gone. Then you have the rest of them. Or if you have a situation where temperature is constant, but moles varies, then you mark off the temperature and keep PV over N, right? That's how you use this equation. You ask yourself first, is it a before and after situation? What are the variables? With a combined gas law, are any of those variables constant from one before and after? If they are, cross them out. And that reduces your combined gas law to a simpler form. So in this case, we've defined what are the individual values, we'll put them in, change the temperature to Kelvin, and here is the temperature in Celsius plus 273. There's your unknown. Then you can solve for it. Okay, now that was before and after. the gas laws up to this point, we've defined them in terms of, we know before conditions and after conditions, and there's a missing variable in there somewhere. But what if you don't know? What if you're looking at the gas as a state function? What is it right now? I don't know how it got there. Are you stuck? Well, fortunately, no. Because what was the combined gas law? It was P1 V1 over N1 T1 equals P2 V2 over N2 T2. How did it get that way? It got that way because this is a constant, and that is equal to the same constant. It's equal to a constant, right? So if we rewrite it and we change the constant, right? This is equal to a constant. We're going to say it's equal to R. R is our constant. Now, if we know what the constant value is, and we know 3 of these, we can solve for the 4th one. Normally, it's expressed in these terms right here. So you would just solve this one for PV on this side, and then move NT over here, N, R, T. Right? So that is the ideal gas law. And this is the ideal gas constant. Now, the one rule that you cannot violate, well, actually 2 rules. Temperature has to be in Kelvin. But whatever the units of measure are here have to be strictly enforced based upon the units for the constant. The units of measure for the constant dictate the units of measure for each of your variables that must be used. If you use a different variable than is in the constant, then the equation falls apart. It doesn't work. So in our case, we're going to be using this one constant, 0.082. I like 0.6 down here instead of 1. Liters for volume, atmospheres for pressure, moles, which is usually constant. I mean, we don't use anything else but moles. And then temperature is K. As long as your units are liter, atmospheres, mole, K, and you use those for the variables, then you will get the right answer for a state function. If you know the constant, which we do, if you know any 3 of these others, you can solve for the 4th. Now, when we say standard temperature and pressure for a gas, what do we mean by STP for a gas? Standard temperature is 0 degrees Celsius, which would be 273 K. Standard temperature. Standard pressure is 1 atmosphere. Okay? So when you see STP for a gas, that's what it means. Later, if we talk about STP for reactions of solids and liquids, then that's a different temperature. That temperature would be 25. But I'll let you know when that happens. For gases, it's 0 degrees Celsius and 1 atmosphere pressure, standard temperature and pressure. So this ideal gas equation gives us molar volume pressure temperature relationship in a state function. So it's not before and after, it's just what is it right now? And if you have the right units of measure, you can find out the answer to your unknown. And this is one of them. Let's see, it's 11 o'clock. I'm not doing on time. This is normally when we would go into the lab. I might only be able to go through section 8. We're up to 0.7 now, so we'll probably get through to 0.8 and then I'll have to stop. Okay, in this case, an automobile tire at 23 degrees, the internal volume of 25 liters, filled with air to a 2.18 atmosphere pressure. What's the number of moles of air in the tire? The first question you need to ask is this a before, after, or a state function? This is a state function. You're only given one temperature, one volume, one pressure. That's it. No before and afters. You know now that you need to use PV equals nRT to solve this problem. So pressure is atmospheres, that's good. Volume is liters, that's good. Here's your constant. Liter, atmospheres, that dictates these units. Moles is going to be our answer. And K is temperature. So you have to convert 23 to K, add 273. Then you can solve for moles, and it's 2.24 moles of gas are contained in that tire under those conditions. What about this one? What's the pressure in a 304 liter tank that contains 5.67 kilograms of helium at 25 degrees? Well, let's see. We have volume. We have temperature. They want pressure. That's our unknown. And they say kilograms of helium. What are we going to do? We need moles, don't we? So how do you find moles from that? Molar mass, right? Molar mass is mass per unit moles. I abbreviated molecular weight. Mass per unit moles. We have the mass, right? We just need to convert it to grams. So it's 5,670 grams. And what's the molar mass of helium? Well, it's around 4. 4 point, let's see. Yeah, 4.00 grams per mole. So moles equals grams divided by molar mass. Now you can plug it into your equation. PV equals nRT, and you're good to go. All right, and we solved the problem. That's 114 atmospheres. That is a lot of pressure, very high pressure. Okay. John Dalton was an Englishman, and he was the one that proposed the kinetic molecular theory of gas. No, the atomic theory, excuse me. He proposed the atomic theory. He also proposed the law of partial pressures. Right? This is a law, it just says this is what happens. He says that when you measure the pressure of a gas in a container, if it is a mixture of 2 or more gases, the total pressure is actually the summation of the pressures of each of the gases contained in that vessel if you were to measure them separately in that same volume. You just add them up, and that's the total. That's Dalton's law of partial pressures. Each of these is a partial pressure for each of the gases contained in that vessel. So in this case, we have pressure for this gas. Let's see. Pressure for this gas is 1. Pressure for this gas is 3. Why? Well, it's got the same volume, it looks like, and it's got 3 times as many molecules, right? So its pressure is 3. And the pressure in here is 2. So when you add them together, the pressure in here should be 6. That's all Dalton is saying. Okay, so let's say we have a gas mixture of oxygen, helium, and nitrogen. And the total pressure is 780 millimeters of mercury. What's the partial pressure of oxygen if we know the partial pressure of helium and nitrogen to be 86 and 124? Here you have an equation, right? Total pressure is equal to the partial pressure of oxygen plus the partial pressure of nitrogen plus the partial pressure of helium. So we know the total pressure is 780 millimeters of mercury. We're given the pressure of helium as 86 millimeters of mercury. And the pressure of nitrogen is 124. There's your unknown. You take this one and that one, subtract it from 780, and you get the pressure of oxygen. (570 millimeters of mercury). It's very simple. Now, here we have a problem that looks like it's unsolvable. We have two vessels containing gas with a valve between them. And you can see the little hole in it is this way through. So they're not mixing yet. They can't mix. This one, and it doesn't matter what the gases are. It's absolutely irrelevant. This one has a pressure of 3 atmospheres and 3 liters total. This one has a pressure of 2 atmospheres and 9 liters total. So let's say qualitatively, what happens when you open that valve? Well, the question is, what's the final pressure? Oh, it does say that they're both helium. So that's okay. They're both helium gas. So when you open it, what's going to happen? Which way is the gas going to move? Is it just going to sit there? Well, what's the driving force? Pressure. This one has a higher pressure than that one. So that one's going to go and squirt some of the helium into this container until the pressures are equal, correct? That's intuitive. So what should the pressure be? Is it going to be greater than 3? No, can't be any greater than the highest pressure. It's going to be less than 3. But it's going to be greater than 2 because you put some more of this over here, you decrease the pressure here, increase the pressure there. So we know it's going to be between 2 and 3. But we want to know exactly how much. Here's the way you solve this problem. You use 2 laws. Dalton's law of partial pressures. You know that the total pressure eventually is going to be the summation of the pressure contributed from this side plus the pressure contributed from that side, even though they're the same gas. And we know how to find the final pressure because of Boyle's law, pressure-volume relationship. Okay, let's see. Do I need to write this one out, or do I have a slide for that? Yeah, I do have a slide for this one. Okay, so here's the approach that you take with this type of problem. You treat this one as if it's being expelled into a vacuum. And then you turn around, and that tells you the contribution to the whole of that gas. And then you treat this one as if it's being expelled into a vacuum. And then you find out what its contribution to the whole is. So now that they're mixed, you just add the pressure from that one to this one, and you find the total. Okay. So what would be the total volume? If this is a vacuum or that's a vacuum, it's going to be the same total volume, right? It's going to be 9 plus 3 is 12 liters. That's the total volume for either scenario. Okay. What's the final pressure for this one? For this one. Well, initial is 2 atmospheres and 9 liters, and a final volume of 12 liters. Right? So P1, V1, and this one is V2. We can solve for P2. So this tells you that if we treat this one as expelling into a vacuum, its contribution to the total is going to be 1.5 atmospheres, less than it was, because it's expanding into a vacuum. Then we do the same thing for this one. And the solution tells us that this one, if it expels into a vacuum, is going to contribute 3/4 of an atmosphere to the total. Then we use Dalton's law of partial pressures. Add them together. Add them together. The final pressure is going to be 2.25 atmospheres between 3 and 2, just like we expected. So now that we've done all the gas laws, we've done Boyle's law, Charles' law, Avogadro's law, the combined gas law, the ideal gas law and its equation, and then Dalton's law of partial pressures. Now we're going to look at changes of state. So we've actually talked about this a good bit already, but a change of state just means a substance changes its physical property. It goes from a solid to a liquid to a gas, or let's put it this way. If this is a solid, this is a liquid, this is a gas, any given substance could go from a liquid to a solid. This we typically say is freezing or solidifying. And if it went back the other direction, we'd say it's melting, right? If it went from a liquid to a gas, we'd say that's evaporation. Or if it went from a gas to a liquid, that's condensation. If it goes from a solid to a gas, that's sublimation. Think dry ice. Right? Changes directly from solid carbon dioxide to gaseous carbon dioxide. And if it went back the other direction, this is deposition. So those are all the possible phase changes that can occur among the different phases. Now, what's the driving force? What causes these changes to occur? Well, there's always a temperature factor involved. Right? If we're going to melt a solid to a liquid, we have to add heat. We heat it and it melts. Or we extract energy from the liquid and it freezes to a solid. Or if we add energy to a liquid, it turns into a gas and we get evaporation. Or if we take a solid and it goes to a gas, that takes energy too. Put energy in. If we take energy out of the gas, it could go directly to a solid. So there are energy transfers there. Very often, another factor that's involved is pressure. And pressure usually influences any changes of gas to liquid or gas and solid. liquid solid usually does not respond to pressure. These are all physical changes. Okay, here we have those. Let's see if I got them all right. Sublimation, deposition, yep. Evaporation, yep. Condensation is there. Melting is there. Freezing is there. Okay, they're all there. I like this triangle diagram because it puts everything in perspective. Well, there's one too. I like this one better. But this also includes a description of which way is the heat flowing. When you go from gas to solid, you're releasing energy. Energy is coming out. So it should get warmer, or it should get colder if you're going from solid to gas. Okay? These processes, the proper term for anything where heat enters the system is endothermic. And this is a good way to think of it. If we have, this is our system, and this is the surroundings, and this is the boundary between them, which way can heat flow? Well, heat can flow in. Right? And that's our abbreviation for heat, that triangle, the delta sign. If it flows in, that means heat is flowing into, and that's endothermic. Surroundings are providing energy to make the solid melt, or the solid turn to a gas, or the liquid turn to a gas. Any one of those three is endothermic. Right? So to go from, say, melting is endo, or sublimation is endo, or evaporation is endo. Energy has to be supplied in order to go through these processes. Absorption of energy. If energy goes the other direction, then you have exothermic. Right? Energy is leaving the system. And when we use this scenario, everything is always in terms of the system. What's happening to the system? Energy is entering the system, endo, meaning into, endothermic. Or exothermic, heat is leaving the system, exiting. Under those conditions, we have these: freezing, condensation, deposition. So this is exo, this is exo, and this is exo. Under any of those conditions, heat has to leave the system in order for those transitions to occur. And if you think of it, what's happening? If heat is leaving the system, the molecules are slowing down, right? So you could go from a gas to a solid, or a liquid to a solid, because now you're removing energy. You're removing the disruptive forces and allowing the potential or cohesive forces to draw things in closer proximity, which means liquid or solid. All right. What's the difference between endothermic and exothermic change and an exothermic change of state? Heat energy is absorbed in an endothermic change. Yep. Endo, heat energy absorbed. And it's given off in an exothermic change of state. Okay. These are slides that just tell you what I've already told you. Evaporation, the process whereby molecules escape from a liquid phase into a gas phase. Okay. the liquid evaporates. Its molecules have to gain kinetic energy in order to do that, overcome those attractive forces. If we increase the liquid temperature, the rate of evaporation should increase. We're putting energy in faster. We're getting molecules transitioning from liquid to gas faster. Let's see. Now, if we're going to talk about liquids and evaporation, this process here, liquid to gas, evaporation. Then if you just set the liquid out on the table in an open vessel, eventually it's just all going to disappear. Right? The liquid will convert to gas until there's nothing left. But if we cork it, if we seal it, then as it starts to evaporate, then what happens is, initially, you have no gas up here from the liquid. You start building up gas. Once you start building up gas molecules here, then they have the opportunity to return to the liquid phase again. They go in both ways, right? Evaporation and condensation. So once you get enough of these in here, then you will eventually reach an equilibrium state in which evaporation and condensation are exactly equal. The rates of each are equal. You've reached an equilibrium. And this will have a characteristic pressure for a given temperature and for a given substance. That's called the vapor pressure. Okay. Now, when you reach that equilibrium, it looks like nothing's happening. Right? The level of liquid has dropped to a certain level. Now it stops. And you don't see any more changes. So on a macroscopic level, nothing's happening. But on the microscopic level, the transition from evaporation and condensation, those rates are occurring at furious paces, just unimaginable rates. But since they're occurring at the same rate, we don't see it from the outside. There's your vapor pressure. The vapor pressure depends on two things. The magnitude of the vapor pressure, which can be measured in any of the units that we've proposed for pressure, millimeters of mercury, atmospheres, pounds per square inch, whatever the case may be. You can measure the vapor pressure. And it depends on two things. Temperature is one, and the nature of the substance is the other. Every substance has its own characteristic vapor pressure at a given temperature. Liquids that have very strong cohesive forces tend to have very low vapor pressure because the forces are holding them in the liquid phase at that temperature. Whereas a substance with very low cohesive forces among the molecules will be more likely to evaporate. So a good comparison is water. Water compared to ether. Okay. Or even ethanol. Right? Drinking alcohol. So this has a low vapor pressure, high vapor pressure, medium vapor pressure. And it all depends on, and this is at the constant same temperature for each one, right? Got to compare apples and apples. At the same temperature, it's based upon the cohesive forces. There's very high cohesive forces, medium cohesive forces, very low cohesive forces. So as the cohesive forces increase, the vapor pressure decreases. Okay. And we often refer to those substances that have very high vapor pressures as volatile. In fact, the EPA, Environmental Protection Agency, and OSHA to a certain extent, Occupational Safety and Health Administration, they identify volatile organic compounds as those organics in the product that are very easily vaporized at room temperature. So these volatile substances tend to have higher vapor pressures. Let's see here. How about this is dimethyl ether, right? This oxygen in the middle means it's an ether. But if we take that same formula, two carbons, 6 hydrogens, and 1 oxygen, right? 1, 4, 5, 6, 7, 8, 9. 8, 9, okay. If we take that same formula and we give it a different structure, right? We say two carbons, 3, 4, 5, 6 hydrogens, 1 oxygen. This is ethanol, the drinking kind, as opposed to ether. The vapor pressure of ether is extremely high. The vapor pressure of ethanol, by comparison, is low. They have the same formulas, they have the same molecular formula, but different structures, which gives them different cohesive forces. This has virtually none, and this has some. All right. A liquid in a closed vessel evaporates for a short time and then condenses as the number of vapor molecules increase. Process is known as physical equilibrium, okay, as opposed to chemical equilibrium. I don't think we're going to get into, well, we might talk a little bit about chemical equilibrium, but we're not going to get into a quantitative approach to that. That's reserved for the general chemistry classes. Boiling. Boiling is a form of evaporation. Boiling takes place when the vapor pressure of the liquid is equal to the atmospheric pressure, right? So if you have a liquid at sea level, then it will boil when its vapor pressure is at and exceeds 1 atmosphere. And that depends on temperature. That's called the boiling point. And that's why water, for instance, boils at a lower temperature in Denver at 1 mile above sea level than it does in Beckley at, let's see, about 2,600 feet. Okay. 5,000 versus 2,500. So it's a higher pressure, which means that it takes a higher temperature to exceed the prevailing external pressure. Okay. So there you have a liquid boiling. And the boiling point is the temperature at which the vapor pressure of a liquid becomes equal to the external pressure that's exerted on the liquid. Okay. The normal boiling point is the temperature at which a liquid boils under 1 atmosphere pressure. It's normalized to 1 atmosphere. So that way you can compare different substances. If you know their boiling points at 1 atmosphere pressure for each of the substances, it gives you a better way to set them side by side and get some insight into their cohesive forces. Okay. Oh, I forgot we had this chart. All right, so at these different altitudes, the boiling point of water is going to change. Let's see. New York City, which is roughly sea level, boiling point is going to be close to 100 degrees Celsius, and the atmospheric pressure will be about 1 atmosphere. But if you go up to, let's say, Salt Lake City, which is a little under a mile high, your atmospheric pressure has decreased by quite a bit, 100 millimeters of mercury or more. And the boiling point is now decreased to 96 degrees. But if you go to the top of Mount Everest, then the air pressure is way down, 240 millimeters, and the boiling point is about 70 degrees. So what does that mean as practical? Well, practically speaking, you need supplemental oxygen. But if you try to boil water up there, the temperature is never going to get any higher than 70 degrees, right? Because during a phase change, the temperature is constant. So if you want to boil an egg on top of Mount Everest, it's going to take you a lot longer than it would in New York City, because you get the water hotter. That's the basic premise behind the pressure cooker. So if you build up a lot of pressure inside that cooker, that means the boiling point of the liquid inside has increased in temperature. And if you increase the temperature, you can cook your food faster. Or if you're using a pressure cooker to can vegetables, you want the temperature to get up high enough to kill all the pathogens that may be lurking in your food while you're canning them. So you use a pressure cooker at, usually they say 20 minutes at 15 pounds per square inch. And if you do that, then you've killed everything inside your food. And once it seals, it's good for however long you want to keep it. But the temperature is much higher at a higher pressure. Okay, there's a definition of boiling point, and we'll move on. What's the vapor pressure of water at 100 degrees C? If it's boiling. If it's boiling, what's the vapor pressure? If it's boiling, the vapor pressure is equal to the atmospheric pressure. And at 100 degrees C, the vapor pressure would have to be on water 1 atmosphere. Because we know that at 1 atmosphere pressure, water always boils at 100 degrees Celsius. Okay, these forces, these cohesive forces that hold molecules together, we refer to those as intermolecular forces. That is, the forces between molecules, not the intramolecular, that is, forces inside the molecule. Those are different. We've already looked at those. Those can be ionic bonds, those can be covalent bonds. These are intermolecular forces between molecules. They're going to be weaker than the forces that hold molecules together. Right? They have to be. If the intermolecular forces between molecules were stronger than the internal forces, what would that do? It would rip the molecules apart, right? So the bonds within molecules must be stronger than the intermolecular forces holding molecules together. Okay, forces within molecules are intra, intermolecular forces between molecules. And I mentioned that. By comparison, the intermolecular forces are weaker than the intramolecular forces. They can be subdivided into dipole-dipole interactions. Actually, we left out one. They can be ion-ion interactions, positive, negative ions. They can be, remember, molecules can have a pole, that is, they can be slightly positive or slightly negative on one end or the other. Right? And those can orient themselves to positive, negative, and those provide some intermolecular forces. But you can have ions bound to ion-dipole interaction are possible. Then the dipole-dipole. For instance, water molecules. Water is shaped like this. This side is slightly negative. This side is slightly positive. Right? So when the molecules of water come close together, they orient themselves with the positive of this molecule against the negative of that molecule, and you get an intermolecular bond, dipole-dipole. This is a special kind of dipole where you have hydrogen involved. Hydrogen and an electronegative atom. Oxygen is good, nitrogen's good, fluorine is good as this atom, right? It needs to be highly electronegative. So it has a dipole in this direction. Right? And it has hydrogen. These are particularly strong dipole-dipole interactions. The strongest of the dipoles. You can have a range of dipole strengths, and that will dictate the strength of the intermolecular forces. Right? Then you can also have much, much weaker forces. These London dispersion forces are temporary. In other words, they only occur for a split second, and then they're gone. So how do we know that they exist? Well, we know that, for instance, nitrogen will condense into a liquid if you get it cold enough. If you remove enough disruptive energy from it, then the dipole interactions will make a liquid out of it. So there must be some force in there, but nitrogen is nonpolar, right? It doesn't have a negative or a positive side. But there are interactions that do hold these molecules together in a liquid state. So there must be something holding them together. And this person is given credit, London, for proposing this mechanism. What he said was, electrons are in constant motion in molecules, and atoms for that matter. So for an instant, you may have a slight distribution of charge toward this side. I mean, just for a microsecond. That's all it takes. Its neighbor then will feel that negative pull Well, actually, it's a push. You've got electrons here. So that negative pushes electrons away from this side and over to this side. Okay? And that instantaneous push means you've got a negative and a positive. A negative and a positive. There's your London dispersion force. Because of the dispersion of electron density for an instant. And then it's gone. We know these forces are very weak because if the temperature is high enough, nitrogen is always a gas. The dispersion forces are too high. The dispersive forces are too high at that temperature. We decrease the temperature, we reduce the dispersive forces enough to where these forces can act, which means they have to be very weak. All right. This is a description of dipole-dipole interaction. And I just told you that with using water as an illustration. The greater the polarity of the molecules, the greater the strength of the dipole. So if you have a very polar molecules in a pure substance, then the forces of attraction are going to be stronger. And they can maintain themselves as a solid or a liquid at higher temperatures because it takes a much greater disruptive force to cause them to melt or to vaporize. All right. Here's an example where you have fluorine and chlorine together in a single molecule, which is possible. They do make these things. Fluorine is more electronegative than chlorine. So you tend to get the negative side of the molecules on fluorine, the positive side on chlorine, and they orient themselves so that they have positive, negative, negative, positive, negative, positive, negative, positive, negative. And you get those intermolecular dipole-dipole forces. This is the hydrogen bond that I described earlier, where you need an electronegative element like nitrogen, oxygen, or fluorine attached to hydrogen. So in nature, in biology, biochemistry in particular, most of the time you have an oxygen. Not all the time, but a large part of the time. You have an oxygen bound to a hydrogen, and this is bound to something else. And that gives you the opportunity for hydrogen bonding. Okay. The more electronegative the element, the stronger the dipole of the bond, and the stronger the hydrogen bonding can occur. We also see that the small size of the hydrogen nucleus contributes. That allows for other molecules to approach more closely. Because what is a hydrogen atom? It's a proton. That's it. It's just a proton attached to something. So that allows them to approach very closely. And the closer you get, the stronger the forces. That's a physical law that we don't have time to discuss now. But the closer you get, the stronger the force, the electrostatic attraction. And that's what this very small hydrogen atom allows for the molecules to approach very closely to one another. This is water. All right, so I drew you an illustration of this, and you see the hydrogen bonding that takes place here, there, 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 there. We use a dotted line. We use a dotted line because it's not a covalent bond. It's not an ionic bond. It's only a slight intermolecular attraction. So how do these forces affect some of the physical properties that we've mentioned before? Vapor pressure, right? If you have a very strong intermolecular attraction among the molecules, you have a low vapor pressure because they much prefer to be in the liquid state. Right? So the vapor pressure is going to be low. Here's an example, hydrogen bonding effect. If we follow the, if we look at these hydrides of the members of the chalcogens, the oxygen family, that would be oxygen, sulfur, selenium, tellurium. The dihydrides of each one of these, we find that the boiling point actually decreases as you get smaller and smaller. Sulfur smaller than selenium, selenium smaller than tellurium. So what you're seeing is, as the molecules get smaller, they can get closer together. Well, actually, the electronegativity matters here. Tellurium is not as electronegative as selenium, and it's not as electronegative as sulfur. So you get a predicted slope in boiling point going this way, and we would expect that water, under the same conditions, would trend toward this place, about minus 75 or 80 degrees Celsius, but that's not true. The boiling point of water is way up here. The only explanation for that is hydrogen bonding. It doesn't follow the trend for that reason. I mentioned London forces before, so I'm not going to spend a lot of time on this one. First of all, London dispersion forces are always there. The reason we don't see them in so many molecules is because the other forces of attraction, the intermolecular forces, are so much stronger that they swamp the effect of London dispersion. Only when the other forces are insignificant or non-existent do we see the London dispersion forces. So water to water, yeah, you get London dispersion forces. But the hydrogen bonding is so strong that the London dispersion is insignificant. You even get London dispersion forces among the noble gas atoms. They're stronger with the larger ones. So xenon is a huge atom. Okay, it has a much higher boiling point than krypton, which is getting smaller. So the smaller you get, the less ability you have for that atom to show uneven distribution temporarily for the electron cloud and give you the temporary polarity that would lead to London dispersion forces. So the smaller it gets, the lower the temperature boiling point. In fact, the coldest substance we've been able to make in bulk is liquid helium. Right? It's very, very low boiling point. All right. Oh, and here we illustrate that. So if we look at the molar mass for radon, xenon, krypton, this is going up the period of noble gases. We find that the boiling point decreases as you go up. That's because the London dispersion forces become less and less and less. Okay. Halogens, however, let's see. Bromine is big, chlorine is big, fluorine, difluorine is big, is smaller. We get smaller as we go up. So the boiling point of bromine is plus 59. That means at room temperature, it's a liquid. Then chlorine is a gas at room temperature, and fluorine has even a lower boiling point. than chlorine. Those molecules are nonpolar, so the only forces available to them are London dispersion forces. Okay, which of these is the strongest intermolecular forces in a liquid? Which is the strongest? Dipole-dipole, hydrogen, London. Well, hydrogen bonding, which is a subset of dipole-dipole, but is the strongest of the dipoles, hydrogen bonding. Which are stronger, intra or intermolecular? The intramolecular forces must be stronger. Right? Because if they weren't, the covalent bonds holding molecules together would be ripped apart. Which one of these has the stronger intermolecular force? Which one is polar? Non-polar, polar. Water would have the strongest intermolecular forces available to it. Okay. And we can also tell from boiling point, right? This is 100 degrees, boiling point. This is minus 195 boiling point. That's a really good clue as to which one has the stronger intermolecular forces. Oh, I mentioned this one earlier. Okay, so this is the slide showing these two molecules have the same formula, but different structures. This one has hydrogen bonding available to it. This one does not. Only London dispersion forces for this one. So it would have the lower boiling point. This would have the higher boiling point. Okay. I didn't discuss in detail, what do we mean by ideal behavior? We mean, for gases, which substance obeys the gas laws. If it's an ideal gas, then there are no intermolecular interactions. They just act like billiard balls, and they act as if they're really not even there. So under what conditions would that be true in real life? Well, think about it. If you've got intermolecular forces at play, then when would they be the least? Right? When would they approach billiard balls? Well, for one thing, if you don't have many of them there in the gas, they would be more ideal because there would be fewer opportunities for them to interact. So low pressure would mean that there will be fewer interactions. Okay, that's one, low pressure. Or if temperature's involved, if you have disruptive forces that are massive, like high temperature, then the gas would behave more ideally. So low pressure, high temperature would minimize these intermolecular forces. And in that case, since nitrogen is a nonpolar gas, it would have less of the disruptive and behave more ideally. Whereas carbon monoxide does have some significant intermolecular interactions. It's a polar molecule. Okay. Oh, this must be toward the end. To hide some helium-filled balloons for a birthday party, you decide to place them in a chest freezer. When you retrieve them, you're disappointed to find the balloons are deflated. As they warm up to room temperature, they return to their original size. So you cooled them down, and what do? Well, Charles' law says if you decrease the temperature, you decrease the volume. So they shrunk. in that freezer. But as they warm up, they expand again. They return to their original size. What gas law is demonstrated? Well, I just told you, Charles' law. And what happens to the kinetic energy of the helium during the warming process? Kinetic energy increases. So Charles' law, yes, kinetic energy increases. Should be that last one. Okay, question 2. All right. A gas water displacement experiment set up, and it's determined, okay, I didn't show you this one before. What's a gas water displacement experiment? Here's the scenario. You've got a reaction occurring in this vessel, right? And it's producing a gas. Say you got a solid down here, and you heat it up like potassium chlorate will decompose to potassium chloride. When you heat it, it will decompose to potassium chloride plus oxygen. So let's see, let's balance that. Let's put a 2 here and a 3 here. And let's put a 2 here. Right. 2 potassium, 2 chlorine, 6 oxygen. There we go. Okay, so this is a gas. These are both solids. Okay. So they're going to stay in the vessel. Well, the gas is going to escape. Right? So we want to find out how much gas is produced for this reaction. Well, the easiest way is to take the tube, right, and put it inside a bottle that's filled with water. Like that. Well, also, it's in a vat of water, like this. There we go. So as the bubbles form in here, they collect at the top, right, and displace the water. So now you've got oxygen up here, plus what? Water vapor. How are you going to deal with that? Because it's not all oxygen, right? So you can't quantify your experiment because you don't know how much oxygen you actually produce because it's got water vapor in it. So what law do we need? Dalton's law. If you know at this temperature that the vapor pressure of water in that space is equal to a certain value, then all you need to do is measure the total pressure inside that vessel, which will be equal to atmospheric pressure, by the way. Subtract the pressure of water at that temperature from atmospheric pressure, and that gives you the pressure of the partial pressure of oxygen in that container. You know the pressure, you know the temperature, you know the volume because you can measure the volume here, right? Temperature, pressure, volume, and you can solve. You know this one, you know that one, you know this one, you know that one. Solve for the number of moles. Okay. So that's setting up this experiment, and that's where this is talking about the experiment. The water displacement experiment. It's determined that 0.81 grams of gas displaces 300 milliliters of water. So 300 milliliters of volume here. Right? And the mass is equal to 0.812 grams. Right? See where we're going with this? The question is, what's the molar mass of that gas? Molar mass is grams per mole. We got grams. We can find moles from the information that's given because this temperature is equal to 20 degrees. And the atmospheric pressure, total pressure, is equal to 750. But the partial pressure of the water vapor is 18. Right, so that's 247 millimeters of mercury is the pressure of the oxygen or the gas that's collected. In this case, it's not oxygen. It's a different experiment. All right, so how do we deal with 742 millimeters of mercury in this equation? You got to convert it to atmospheres, right? So 1 atmosphere equals 760 millimeters of mercury. Okay. If we multiply that times 742 millimeters of mercury, then that'll give us atmospheres because these two cancel. Now you've got atmospheres that you can put in here. You got volume that needs to be converted to liters, right? 0.3 liters. Put it in there. Or 0.0821. Temperature is 20 degrees plus 273. Now we've got everything we need. Solve for moles. And then put moles in the expression for molar mass would be 0.812 grams per how many moles? Oh, we're working it out here. Okay. So here's what we're given. We got grams. We got that many liters of volume. We got this total pressure. We got that temperature. The water pressure is 18 millimeters of mercury. That's vapor pressure at 20 degrees. So now we have 0.973 atmospheres after we subtract 18 from it and convert it to atmospheres. There we go. So we're going to solve for moles. There's your atmospheres. There's your volume. There's your gas constant. There's your temperature. 20 plus 273 is 293. And this is the number of moles. Put the number of moles in here. There it is. And you get 58 grams per mole. Okay. That took a lot of work, I'll grant you. But it's doable. And actually, when you get the answer, it's satisfying because that's a real world scenario. That's what chemists do in the lab all the time. Determine the molar mass by this method. Okay, that's it for chapter 7.